Today we're continuing on with this discussion of frequency modulated AFM. And I thought today I would focus a little bit more on the experimental details to sort of complement what I discussed in last lecture. So if you were here last time, what we did is we tried to give you some sense of the fact that the frequency of a cantilever will shift from its resonance value when the shape of the potential well that it oscillates in starts to acquire non-symmetric aspects, non-symmetric terms. And for the case, to apply that to the case of atomic force microscopy, we ended up with this formula that was first derived by Sater and Jarvis, which is really the fundamental formula for frequency modulated AFM. And it basically says that if you locate a tip at some equilibrium position D star from some arbitrary position D equal to 0, and if you then allow that tip to oscillate with an amplitude A about that equilibrium position, over time the tip will sample the well, the tip sample interaction force potential in the way that I've drawn. How much of the interaction force is sampled, of course, depends on the amplitude A of the cantilever. That's something that experimentally you can control. And what Sater's formula tells you is, it tells you what the magnitude of the tip sample interaction force is at the minimum separation of the tip from the substrate. So that's what this formula at the bottom of the slide tells you. And that tip sample force interaction at the minimum separation between the tip and the substrate, that's related to the amplitude of the oscillation of the cantilever, and it's also related to the frequency shift of the cantilever as it moves from a position far from the substrate to this position D star. So in Sater's formula, this dummy variable C, that's what's integrated over, and it's integrated from the minimum value, minimum separation distance between the tip and the substrate, all the way out to infinity. Right now, it's integrated out to infinity to make the integral a little bit easier to handle. The point is, the further away you get from the tip sample surface, the interaction force goes to 0. If the interaction force goes to 0, then this parameter capital omega, which is the fractional frequency shift, right, is a function of z. That fractional frequency shift also goes to 0. So pretty much there's very small contribution when you integrate past values of C greater than, let's say, D star plus A. Now this formula has a couple of important parameters. One parameter is the spring constant of the cantilever. That's the multiplicative factor in front. There are three terms in the integrand. The first term in the integrand is the term that's appropriate for small amplitude oscillation. That constant 1 in the integrand is multiplied by the fractional shift in the frequency, capital omega, right? And that is just a small amplitude formula that was derived at the end of last, or wasn't derived, it was presented at the end of the last lecture. As the amplitude gets larger, these other terms start to contribute. The third term in this expression represents the contribution when the amplitude of oscillation becomes large, when the tip amplitude starts to become large. The term in the middle is kind of like an interpolation term that bridges the gap between small amplitude and large amplitude. But what this formula tells you is that if you systematically do an experiment where you position the tip at a certain value of D star, and if you happen to know the amplitude of oscillation of the cantilever, then you can infer what the tip sample force is at the position D min. Right? So by systematically moving the cantilever closer and closer to the substrate, measuring the amplitude and frequency shift at each value of C that you stop, you eventually can map out the tip sample interaction force. So all these theories that we were discussing early in the semester, where we had van der Waals forces, we had DMT, we had Hertz contact, all these models for the tip sample interaction force, those models can in a certain sense be validated with this FM-AFM approach. That's why it's so interesting. So you say to yourself, well, that's cool, that's worth doing. The question is, how do you actually do it experimentally? And that question was asked in the, let's say, mid-1990s, and a variety of groups worldwide started to investigate how to accurately measure the frequency shifts of cantilevers, and how to do that is basically going to be the topic of the lecture today. There should be a few obvious requirements that are needed to make this experiment work. One is you need reasonably high stability, because as you slowly move the cantilever closer and closer to the substrate, you don't want drifts between the substrate and the cantilever to set in. So you need to have a reasonably stable system such that you can systematically approach the sample with the cantilever and not be plagued by thermal drifts, right? So these experiments take a little bit longer to perform than, let's say, the typical constant amplitude experiments that we've discussed in tapping mode AFM. So that's the reason why the high stability is required. The frequency shifts that occur as the cantilever comes closer to the substrate, those frequency shifts are small. They're on the order of maybe 0.1% to a few percent of the frequency of the natural frequency of the cantilever. So if the natural frequency of the cantilever is 100 kilohertz, you're often measuring maybe 1 hertz shift out of 100 kilohertz, or 2 hertz shift out of 100 kilohertz. So you need a technique to accurately measure frequency shifts, and we'll discuss that a little bit. There's very good ways to do that now. And then the third thing that should be reasonably apparent after the homework set that you've already gone through, right, is you want to avoid this jump to contact that occurs when the slope of the tip sample force interaction curve, when the slope of that matches the slope or matches the spring constant of the cantilever, right? When that slope of the tip sample interaction force matches the cantilever spring constant, then that red line is tangent to the tip sample force at some particular tip sample separation. And when that occurs, there are two stable solutions. There are two stable positions of the tip, right? The tip can then jump into contact. And you clearly want to avoid that if you're trying to measure the tip sample interaction force as a function of, let's say, tip sample separation. So one way to do that is to pick a cantilever with a really stiff spring constant. If you pick a cantilever with a really stiff spring constant, then the cantilever F versus Z curve indicated by that green line in this diagram, that will only intersect at one point along the tip sample force. And if it only intersects at one point, then there's only one stable solution for all tip sample separation. So you avoid this jump to contact that we discussed earlier in the amplitude modulated AFM part of the course. So these are three requirements that knowing what you've already been through in this course, you probably might have been able to surmise, right, is requirements in order to pull this frequency modulated AFM experiment off. So the new idea that emerged again in the mid-1990s was to abandon the traditional cantilevers, the traditional microcantilevers that were commercially available at the time. The reason those cantilevers were abandoned was because their spring constants aren't stiff enough. And they also do not possess the necessary stability to allow these experiments to be conducted. I'll try to explain that in a little bit more detail later on. And a number of groups in the world, in particular Franz Giesbel in Austria, came up with the idea of using these tuning forks as cantilevers, right? And tuning forks have a lot of advantages over commercial cantilevers. The first advantage is they're made by the millions, right? And everybody has a tuning fork in their wristwatch to keep time, right? So most wristwatches today use tuning forks. This idea goes all the way back to the 1960s when this watch company Bulova marketed this watch called the Accutron. It was a revolutionary watch at the time. It was based on a tuning fork, kept very accurate time over days and days and days. Before that, you were constantly resetting your wristwatch because it was hard to maintain an accurate frequency or an accurate time standard internal to the wristwatch, but that changed in 1960. And if you open up your wristwatch and look, you'll find a little canister buried inside, and that canister contains a tuning fork. So if you carefully cut away the canister, pull it away, you'll find a tuning fork with electrodes on it, pretty much like the pictures that I've got shown here. The advantage of the tuning fork is, one advantage of the tuning fork is that it's extremely cheap. They're about 25 cents each. So you can go to any electronic company and you can buy 50 or 100 of them and you're going to pay just a few dollars. And the reason they're so cheap is because they're used everywhere in the world for wristwatches. They're also used in your computers for timing, right? They're an extremely accurate time base. The cantilever that's probably most interesting for frequency modulated AFM is the tuning fork that's most useful for frequency modulated AFM is a tuning fork that's been designed to operate at a frequency equal to 2 to the 15th hertz. Right? 2 to the 15th hertz is about 32 kilohertz, and this frequency is then used as a clock frequency for many electronic circuits, right? So the data that I'll show you today is based on a 32 kilohertz tuning fork, but in principle you can buy tuning forks that have a variety of different frequencies. It just depends on the design of the tuning fork itself, right? So this is kind of like everything you wanted to know about tuning forks in one lecture. Tuning forks are made out of quartz, right? Quartz is crystalline SiO2. And apart from silicon, I think quartz is the second most, is the second material in the U.S. by weight that's made every year, right? Silicon by far is the leader. But after that, I think quartz comes in close second. And the reason quartz is so interesting is because it's a piezoelectric material. So the piezoelectricity, if you're not from material science, right, you don't have a material science background, but piezoelectricity means that if you push on the quartz, charges develop on the surface of the quartz due to the mechanical stress that you impose, right? And so it's a way of coupling mechanical forces to electricity. The phenomenon was actually discovered in the 1880s in France. Well, using quartz crystals, they just noticed that if they took a quartz crystal and placed weights on the crystal, a voltage would develop across the plates, across the faces of the quartz. Right? That was the first observation of piezoelectricity. Right? Since then, we've learned an awful lot about quartz. We know it can be made in a crystalline material. If it's made in a crystalline material, then it can be oriented. And this piezoelectric behavior that translates force into voltages, right, that can be optimized by identifying the appropriate axes, the appropriate crystalline axes in the quartz single crystal. So it turns out there are three important axes in quartz and single crystal quartz. One axis is referred to as the mechanical axis. In this plot, that's referred to as the Y direction. There's an electrical axis referred to the X direction in this plot, and then there's a optical axis referred to the Z direction. Now, the optical axis has a threefold rotational symmetry associated with it. Right, so every 120 degrees, if you rotate the crystal every 120 degrees, you basically have the same crystalline structure, right? The optical axis isn't so important for piezoelectricity. What is important is the X and the Y axis. And so what this diagram is trying to show you is that if you put pressure, if you squeeze the quartz crystal along the Y axis, then a voltage develops across the faces oriented perpendicular to the X-axis. And that's just, those orientations are just experimentally determined. So once you know those three crystallographic directions, then you can start to cut quartz wafers from the single crystalline quartz. And the orientation of these various quartz wafers have been optimized for different purposes, right? Depending on the slab, the thickness of the slab that you cut, that controls the resonant frequency of the quartz, right? And depending on the orientation of the quartz crystal, you can get longitudinal or shear stresses that develop when you apply a voltage across the electrical axis, or conversely, if you apply a force along the mechanical axis, you can get voltages along the X-axis. Right, so it turns out the tuning fork, right, the optimum orientation for the tuning fork is shown in this diagram. And so all the tuning forks in the world are somehow cut from single crystalline quartz to have this orientation with respect to the X, Y, and Z crystalline axes. Okay, and there are millions of these things produced, right? It's a mammoth industry. Why is quartz so useful for AFM purposes? Actually, why is it useful for frequency standards, right? The reason it's so useful for frequency standards is that depending on how these quartz crystals are cut from the single crystalline quartz, they can be basically, their dimensions can be made basically immune to small changes in temperature, right? So those different cuts that were shown in the previous slide, those cuts were determined by insisting that once the crystal is cut with that orientation, you don't want the dimensions of the crystal to change very much as the temperature changes by, let's say, 10 degrees, right? If the temperature doesn't, if the dimensions of the crystal don't change much with temperature, then clearly as the temperature of, let's say, your wristwatch changes as you go from inside a classroom to outside where it's cold, right? If the frequency doesn't change much, then it keeps accurate time. That's the basic idea. And of course, when you apply that concept to AFM technology, it basically means that you don't need to wait for a long period of time for your cantilever to stabilize, right? It's reasonably immune to temperature drift. And that's illustrated in this graph here, which compares the change in frequency divided by the resonant frequency of quartz and silicon over a narrow temperature range around room temperature. Right? So experimentally for these quartz crystals, right, the change in frequency with respect to a small change in temperature is on the order of 0.04 parts per million per degree centigrade. Right, 0.04 parts per million per degree centigrade. And if you compare that to silicon, the effect is quite striking, right? So variations in temperature of these quartz tuning forks by, let's say, plus minus 10 degrees barely changes the resonant frequency. And if you compare that to, let's say, a silicon microcantilever, right, the effect is quite stunning, right? So the results from silicon are shown by the dashed line. So there's real good reasons to choose quartz to do frequency modulated AFM, right? And in fact, it's surprising to me that cantilevers, conventional cantilevers, aren't fabricated out of quartz, because if they were, they would be a lot more stable. I think the difficulty is it's just hard to attach tips to quartz cantilevers, where with silicon it's very easy to do that using the microelectronics etching technology that's evolved over the last 50 years. So quartz is great, it's thermally stable. If you cut a piece of quartz into this tuning fork geometry, which I indicated schematically over here, it's important for you to apply voltages to that tuning fork in such a way that you cause the tuning fork to oscillate in one of its two primary modes. So there's a symmetric out-of-phase mode, and then there's a symmetric in-phase mode. Most tuning forks are cut with electrodes that cause this in-phase mode to be excited. And the way that's done is it's done by carefully wrapping electrodes, gold electrodes, around the quartz tuning fork in the way that's indicated in this diagram. So there are two electrodes shown schematically. One is labeled 1, the other is labeled 2, right? And if you apply a voltage V12 between those two electrodes, the electric fields that are set up inside the quartz crystal are designed to excite this in-phase oscillation, right? So that all comes prearranged for you. That's all been worked out 50 or 60 years ago, right? So it's a really neat package, because the in-phase mode of oscillation, where the tines of the tuning fork oscillate in phase one with respect to another, right? That motion is excited at the frequency omega of the voltage that you apply. Now, if you just pick any old arbitrary voltage or any old arbitrary frequency and apply a voltage between the tuning forks, the amplitude of this motion is going to be very small, right? What you need to do is you need to find the resonant frequency of the tuning fork. The resonant frequency of the tuning fork is going to be controlled by the dimensions. So L, W, and T, right? The dimensions of the tines of the tuning fork will then allow you to adjust where this resonant frequency occurs. And as I said earlier, the tuning forks that I like for AFM applications, those tuning forks have been cut, have been designed to produce this 2 to the 15th hertz oscillation, this 32 kilohertz oscillation. So the prediction is that if you apply a voltage at this 32 kilohertz frequency, this 2 to the 15th hertz frequency, then the tines of these tuning forks will oscillate back and forth with high amplitude, because you've reached the resonant frequency of this particular structure, right? So tuning forks have tuning curves just like regular cantilevers do, right? You have to sweep the frequency of the applied voltage. Your AFM controller has to be able to pick out the amplitude of the quartz, of the tine of the tuning fork. It has to be able to measure that amplitude, right? And when you reach this resonant frequency, the amplitude of oscillation will be a max. That's the resonant frequency, and that's the frequency that you're going to use when you do AFM experiments, just like when we did amplitude modulated AFM. So there are many similarities. So what does the vibration spectrum look like? So these are some of the data that one of my students, Chin, took while he was here at Purdue. The tuning forks, when you buy them, are encased in this little canister. And this canister usually is evacuated, so there's no air inside. And the reason they want no air inside is because they don't want any damping of the tuning fork by viscous damping due to the air. So if you just buy the tuning fork commercially and you apply a voltage, you sweep the voltage, measure the current through the tuning fork. So the tuning fork now becomes an electronic device. and you actually measure the current that flows through it, you find that the current that flows through it is maximum at this 32 kilohertz. It has a very high, a very sharp resonance compared to an amplitude modulated silicon cantilever. So AM, AFM cantilevers is used for intermittent contact AFM experiments. The Q factor, that resonance, is on the order of a few hundred. Q is a few hundred for a conventional silicon microcantilever. These quartz tuning forks, because they're crystalline, very few defects. Right? It's single crystalline SiO2. There are very few defects. The tines that oscillate, okay, are considerably thicker than the thickness of a silicon cantilever. So that means that the energy loss to the supporting structure of the tuning fork goes way down, and as a result, the Q goes way up. So if you eliminate this damping due to air, right, you end up measuring Qs that are on the order of 64,000, right? Really large. When you take the tuning fork out of the can and you run the tuning fork in air, right, the frequency downshifts a little bit. It's indicated by the red curve, right? Why does it downshift? It downshifts because there's added mass now to the tines of the tuning fork due to the air molecules that surround it. If you add mass to the tines of the tuning fork, it shifts the resonant frequency to lower values. And also the Q of the tuning fork drops. It drops by about a factor of 10, but it's still on the order of 9,000 in air, operating in air. And you compare a Q factor of 9,000 to a silicon Q factor of a few hundred, right? You can clearly see that there are going to be huge advantages, for instance, to measuring the position of the peak in that tuning curve as, let's say, the tuning fork is brought closer and closer to a substrate, right? So the sharper the Q of the resonance, the easier it is to measure small changes in frequency. And of course, that's what we need to do for frequency modulated AFM. So, the model of the tuning fork that we've used in our lab is this Raltron R26 tuning fork. These are the parameters that we measured by taking one of the tuning forks out of its can. We've inferred a spring constant of about 12.7 kilonewtons per meter. This should be compared to the spring constants of 40 newtons per meter that are typical for intermittent contact AFM cantilevers. So this is a really stiff cantilever compared to the cantilevers that we've dealt with in the past, right? But we need that stiffness because that basically means that the tip that we're going to attach to one of the tines of this cantilever, this tip is not going to jump to contact. It's not going to exhibit the SPI stability that conventional AFM cantilevers exhibit. That's also a huge advantage, right? So, the resonance that we measure experimentally is now no longer measured by a laser beam bounce technology. So another distinct advantage of these quartz tuning forks is you can throw away that laser diode, right? You can throw away the photodiode that collects the laser light that bounces off of a conventional silicon cantilever. You don't need that anymore. This quartz tuning fork is like an electronic circuit element. And what you do is you can sweep the voltage across the electrodes of the tuning fork and you can measure the current that flows through the tuning fork. And when the current that flows through the tuning fork has its maximum value, then you've reached the resonant frequency of the tuning fork. You no longer need to direct a laser beam off the cantilever. Huge advantage if you're trying to do experiments in vacuum, right? Because if you're going to do experiments in vacuum, you have to worry about the outgassing of the photodiode. You have to worry about outgassing of the laser diode that's used to illuminate the cantilever. Here, all you have to do is put the tuning fork inside of a holder, insert the holder into a vacuum chamber. You're going to need 2 electrodes, two wires coming out, right? So you eliminate all the hassle with lasers to pull this off. So what this is a plot of is the plot of the current through the tuning fork as a function of a voltage. It's probably about 5 or 10 millivolts applied to the tuning fork, which is systematically vary the frequency of the voltage. We see a very nice peak in the current that flows through the tuning fork. Currents are on the order of 50, 60 nanoamps, right? This peak has a funny shape to it. It's not governed by the physics that was described for the resonance of a silicon cantilever, right? So the resonance of a silicon cantilever is governed, the shape of the resonance of a silicon cantilever is governed by the way that silicon cantilever is excited. There are 2 modes of excitation. One mode of excitation is you cause the base of the cantilever to vibrate at a fixed frequency, and you vary that frequency and measure the response of the cantilever. Right? That's called the base excitation mode, and that base excitation mode gives rise to a certain characteristic resonance line shape that we've discussed about a month ago. The other mode of oscillating a standard silicon microcantilever is to coat it with iron film using an external magnetic field to cause the microcantilever to oscillate. And that mode of excitation causes a characteristic line shape also. We discussed that about a month ago. This quartz tuning fork produces yet another characteristic shape for the resonance curve. It has a sharp peak, but it also has a very shallow minimum on the far side of the peak. And the reason this curve has this shape is because it's an electronic component, right? And electronic components or electronic circuits can have various shape resonances. Basically what's happening is the current through the tuning fork peaks when the impedance of the tuning fork reaches its minimum value, right? And this anti-resonance, this shallow dip in the resonance curve at frequencies greater than the resonance frequency, that occurs when the tuning fork has its maximum impedance, right? And the reason tuning fork can have a minimum and a maximum impedance is because the circuit model for the tuning fork involves 2 parallel branches, as I've indicated schematically in this picture. The upper branch is the upper branch that models the actual tuning fork itself has a capacitance, an inductance, and a resistance that have to be determined for each tuning fork that you use, for each class of tuning forks that you use. If the equivalent circuit for the tuning fork were just related to that upper branch of the equivalent circuit, that anti-resonance would go away, and the tuning fork would have a nice symmetric resonance curve. But there are always some parasitic capacitances floating around. Those parasitic capacitances are modeled by this capacitor C sub P, and that capacitor C sub P is in parallel with the lump models, the lumped electrical models for the tuning fork. And it just basically means a current through the tuning fork can occur in 2 different paths. Okay? And when the current through the upper path and the bottom path, when those 2 currents are in phase, right, then the impedance is a minimum and the current through the tuning fork is a maximum. When the current through the bottom path is precisely 180 degrees out of phase with the current through the top path, right, then the impedance of the tuning fork that the applied voltage sees, right, that impedance is a maximum, and that means that the current through the tuning fork is a minimum. Right? So whenever you see a resonance curve in an electronic circuit, right, the take-home message is, at least whenever I see a resonance curve in an electronic circuit that has this peak followed by this shallow minimum, right, that's telling me that the equivalent circuit has to be modeled by two parallel paths. Right? When the current is flowing through those two parallel paths, and of course the phase of the current with respect to the applied voltage, that shifts in interesting ways that has to be worked out in detail by solving for the impedance of this equivalent circuit as a function of frequency. So our electrical engineers in the audience, they know how to do that very well, and when they do it, you can reproduce the shape of that resonance curve very nicely, right? So all these fine details, right, it's reasonably important to at least appreciate where they come from, right? You see these things when you do the experiments, but what you then have to do is go home at night and try to understand what produces those features. It's very easy to eliminate this parasitic capacitance, right? So that anti-resonance feature could be confusing when you're trying to interpret data. So it's useful to try to eliminate it, and one way to eliminate it is to build a compensating circuit. It indicates schematically how we did that when Shin did his PhD work here at Purdue. He basically built a simple op-amp circuit with an adjustable capacitance in the lower leg. That adjustable capacitance can be changed to null out the effect of the parasitic capacitance, which technically you don't know, right? You can't, ahead of time you don't know what that parasitic capacitance is going to be. So you have to put in an adjustable capacitor. You have to tune that adjustable capacitor. And as you tune that adjustable capacitor so that you eliminate the parasitic capacitance, then you can recover a very nice symmetric resonance curve. And then once that's set, right, then you can use that very symmetric resonance curve to interpret any experimental data that you get. It just simplifies the interpretation of the data. So that's also been implemented in the course of the experiments that I'm going to show you at the end of this lecture. It's a fair question to ask, how do you calibrate the amplitude of the tuning fork tine as a function of the applied voltage? Right? You can measure the current that flows through the tuning fork as a function of the applied voltage. And you can do that at different frequencies, but how do you actually measure the amplitude in nanometers that the tuning fork oscillates at? So this problem is equivalent to the problem of converting the voltage in the position-sensitive photodiode, right? You want to convert that voltage to a displacement in nanometers, right? So we talked I think there was a whole lecture devoted to that calibration in AM AFM about a month ago. You have to go through a similar calibration here, and the way we did it was to build a simple laser interferometer, right? And the idea is sketched in the bottom right-hand panel of this slide. This laser interferometer basically takes infrared light. It directs it through a small fiber optic. That small fiber optic is placed a small distance above one of the tuning fork tines. Right? There's an intensity I that comes through that tuning fork, or comes through that fiber optic. And that light is then reflected at 2 points, 2 places. One place is the end of the quartz fiber, and that's indicated by the back arrow labeled R2. So some of the light that's contained in the fiber optic is reflected at the interface R2, and some of it actually emits into air and then is reflected by the top tine of the tuning fork, and that's indicated by the coefficient R1. And depending on the separation of the fiber optic from the tuning fork, the relative phases of R1 and R2 can be varied. And if the relative phases of the reflected light can be varied, then you can set up an interference, right? A standing wave interference in this optical interferometer. And that standing wave interference then shows up as a voltage on a photodetector that's indicated in the upper left-hand region of this diagram. So the idea is you buy one of these commercially available laser photodiodes that run at about 1,300 nanometers. These are used for all types of communication purposes, so they're really cheap, right? This fiber optic interferometer, you can buy that for a few $100s from almost any optical science company. And you can set up one of these interferometers to actually calibrate small changes in the position of the tine of the tuning fork with respect to the fixed position of the end of the fiber optic, right? So that's the basic idea behind it. The implementation is pretty straightforward, and what you find is that if you mount your tuning fork, I think I illustrate this on the previous, right? If you mount your tuning fork on a little piezo tube as indicated, then by applying voltage to the piezo tube, you can systematically move the tuning fork up and down with respect to the fixed position of the fiber optic end, right? And so as you apply voltage to the piezo tube and you look at the voltage of the photodiode, right, you get a curve that looks something like this, where it goes through maximum and minimum. This is your interference minimum and maximum of the light that's reflected from these two surfaces, right? And it turns out that the separation between the maximum of 2 points on this curve is just precisely lambda by 2, where lambda is the wavelength of the photodiode that you use to run the fiber optic interferometer. So that number is known with very high precision, and that allows you to calibrate the position between two peaks in this interferometer, right? The two peaks is 655 nanometers. And then that allows you to put a voltage on the tuning fork and watch how the voltage on the photodiode changes, right? So as the position of the tuning fork tine with respect to the end of the fiber optic, as that position changes, this black dot will move up and down on this sinusoidal curve. And how much it moves up or how much it moves down can then be calibrated, because you know the separation between these two peaks is 655 nanometers. So by doing a sequence of calibration curves, you can actually calibrate the amplitude of the tuning fork tine as a function of the voltage that you apply to the electrodes of the tuning fork, and you can get that calibration as precise as you believe the 655 nanometers of your laser photodiode that you use in this fiber optic interferometer. Well, once you know that number, right? Once you know how many millivolts applied to the tuning fork corresponds to how much amplitude of oscillation of the tuning fork. Once you know that number, then you're fixed. You're set, right? That's the important calibration number. And what we've learned is that once you calibrate a tuning fork, its calibration remains very, very reproducible. You can buy dozens of tuning forks from the same company. You can check the calibration of dozens of tuning forks, one with respect to another, and not surprisingly, the calibration constants are all the same. So once this calibration is done very carefully in a lab, right, that calibration number can then be used with pretty high confidence to characterize the displacement of a tine of that tuning fork, same model number, same manufacturer, right? That you got it licked, right? You got the problem solved. You don't have to calibrate every tuning fork that you use. Once you know the number, it's pretty pretty good for all tuning forks of that model. And of course, the reason that's true is because there's so many of these tuning forks made. They're all made identical, one with respect to another, right? All these problems that you have with the silicon microcantilevers, that kind of just disappears. So there's a lot of advantages. So the next thing you need to do, right, to implement this FM-AFM experiment is you need to attach a tiny tip to the bottom end of one tine of this tuning fork. And the way we did that was we actually snapped off a conventional microcantilever, and we then, using a viscous glue, we then stuck that, a small amount, right, a small amount of viscous glue allowed us to stick the a conventional AFM cantilever onto the bottom tine of a tuning fork. And so therefore we were able to produce essentially a sharp tip mounted on the end of a tuning fork. That sharp tip can be resonated now at 32 kilohertz. We can achieve Q factors in air of about 9,000, and we're now in a position to allow that tip to approach a substrate, and we're going to measure small frequency shifts in the resonance frequency of the tuning fork due to the interaction of that tip with the substrate. So that's the idea. That's the idea. I'll say that commercially these tuning forks come pre-mounted on ceramic plates. So this is an example of the so-called Q plus sensor that's available from Franz Giespel's company. Right, Giespel pioneered these tuning forks in frequency modulated AFMs. He started a small company that sells these tuning fork sensors, and so you can see here what you get when you buy a Q plus sensor. It's basically your quartz tuning fork with electrodes plated on it in the appropriate way to cause this motion of the tuning fork tines. There's a sharp tip mounted on the end of the tuning fork, and this then mounts into the head of an AFM in such a way that the tip is pointing down towards a substrate, right? So then you have to approach the substrate towards the tip using all the techniques that normal AFMs use, and you now are in a position to measure the shifts in the resonant frequency of the tuning fork due to the tip sample interaction just by measuring the current that flows through the tuning fork. You no longer need to use this laser to bounce off the tine of the tuning fork into a photodiode. It's an electrical measurement now. It's much cleaner. How do you measure frequency shifts that are small compared to, let's say, a reference frequency of 32 kilohertz? How would you do that experimentally? So this is probably the most important slide of the lecture because it tells you about phase lock loops. So if you don't know about phase lock loops, let me tell you, they're pretty amazing little pieces of electronics. They became commercially viable in the late 60s, early 70s, with the advent of integrated circuit technology. And what they basically do is they take a signal that's noisy and sinusoidal. So you have an input signal that may have noise on it, but it oscillates at an amplitude A. It's got a certain frequency omega, and it's got an unknown phase phi, right? You don't know what that phase, and you don't know what that frequency omega is. And the purpose of this phase lock loop is to produce an output signal that has a frequency and phase that exactly matches the input frequency and phase that you do not know, right? And of course you want to do this in a short period of time. So you need a feedback loop that automatically adjusts omega naught and phi naught until the match between omega naught and phi naught and omega and phi are very good. And then once that match is good, you want that phase lock loop to track small changes in frequency omega, small changes in phi, automatically in a feedback mode, right? You don't want to have to go and measure on a frequency counter what the new frequency is. You just want a signal that comes out which tells you what that new frequency is. And that's what this phase lock loop does. It involves three components. Very briefly, it involves a phase detector, which is labeled P sub D. This phase detector compares a reference frequency from a voltage-controlled oscillator. It compares that reference frequency to your input frequency, and it produces a DC output that's proportional to the phase difference between those two signals. And the phase lock loop is instructed, it's programmed in such a way as to make that DC output go to zero. When the DC output goes to zero, that's telling you that the input frequency, omega naught, and input phase, phi naught, from this voltage-controlled oscillator matches exactly the omega and phi of your unknown signal, right? And so this DC voltage is then passed through a filter. The filter tries to get rid of the noise. That output of the filter is then fed back into a voltage-controlled oscillator. This is a chip that you can buy. If you put a DC voltage into the chip, it produces a sine wave with a frequency that's proportional to the DC voltage, right? So it takes a DC voltage in and it gives you a frequency out. The frequency out depends on the DC voltage in, right? So this all can be done in a feedback loop mode of operation. And basically what happens is you put your input frequency in, you turn the feedback loop on, you activate it, and within a second or two, you hope you get a lock condition in which the omega naught and phi naught are now locked to omega and phi. And if omega and phi varies with time for whatever reason, right, this feedback loop is instructed to change omega naught and phi naught in order to keep this lock, right? So the omega naught and phi naught, that's something that you can measure, right? That's a clean signal. You can measure that with a variety of different techniques. And in this way, you're ensured that you know what the input omega and the input phi is, even though it may be a very noisy signal, right? So it's a really cool technology. I have a whole bunch of notes that if you're really interested in this, you can read. I don't think it's worth going through that, but it tries to summarize the important features of these phase lock loops. One of the assumptions, I'll say, is that you're assuming that the frequency shift of omega is not very large, right? So if the frequency shift of omega is factors of 2 or 3, this phase lock loop is not going to work. It will not be able to track those large of change in frequencies of omega. But if the frequency change in omega is a few percent, right, then these phase lock loops have a dynamic range that allows them to track those small frequency changes. It also assumes up front, these phase lock loops also assume up front that you know roughly what the input frequency is. Right? So you can't just put any old frequency in. You got to know it's an input frequency within a certain range. And a certain range is determined by the way the feedback loop and the phase lock loop works. Right? So you need to know certain things, but once you know those things, right, you need to know roughly the input frequency, and you got to know that the input frequency doesn't change much during the course of an experiment. Then these things really work well. To do this with accuracy, I will just mention that you need a 24-bit voltage-controlled oscillator, right? You can't use 8-bit, 12-bit, 16-bit. That won't give you enough accuracy. So one of the problems of implementing this is that these voltage-controlled oscillators have to have like a 24-bit precision signal put into them. That means that the voltage that goes in has to have 24 bits of control. Otherwise, you will not have the ability to determine very small frequency shifts. So that's another thing that has to be known when you use these. But once you have that phase lock loop in place, then you're in business. The phase lock loop is basically part of this feedback, this PI feedback loop mechanism, right? We've described our tuning fork. We've put a tip on the end of the tuning fork. We drive the electrodes of the tuning fork with an AC voltage source. That AC voltage source is adjusted so that the frequency of that voltage source is very close to the resonant frequency of the tuning fork. So the tip attached to the end of the tuning fork now oscillates at this 32 kilohertz, right? And what we do is we basically drive the substrate towards the tip, and we try to do a variety of AFM type experiments, right? So there are basically two modes of operation for these frequency modulated AFMs. The first mode of operation is use the frequency of the tuning fork as your feedback parameter. And as you scan the tip over the substrate, the interaction between the tip and the substrate will cause small changes in the resonant frequency of that tuning fork. And what you would do is you adjust the position of the substrate with respect to the tip to keep the frequency, the resonant frequency of the tuning fork fixed. Right? So these are referred to as constant frequency images, and the feedback parameter is the frequency of the tuning fork. Your feedback controller does whatever is required to keep the frequency of the tuning fork fixed as you scan over the substrate. And in the process of doing that, you basically are mapping out a constant frequency image of the substrate. And it turns out, as I'll show next lecture, right, these constant frequency images of substrates that if the substrate is atomically flat and well prepared, these images are capable of atomic resolution. So you can actually see individual atoms on a substrate with this constant frequency imaging technique. Now, it was thought that the reason you could see atoms in frequency modulated AFM, right, it was thought that feature of FM AFM resulted or was a consequence of the fact that the resonant frequency of the tuning fork was very sharp. Right? So you recall I commented tuning forks in air have Q factors of 9,000. If you put them in a vacuum, the Q factor increases to 50 or 60,000. So that means that the resonant curve is extremely sharp, and that allows you to track very small frequency changes with high precision. That's what a sharp resonance curve translates into. And so the standard argument has been for many years that you see atoms with frequency modulated AFM, and you routinely, if you run these things in ultra high vacuum, you routinely see atoms. It's not like you just see them once a day or once a month. They're always there. Right? The argument has always been that capability is related to the high resonance or the high Q values of the resonance for a tuning fork. That wisdom is being challenged now because various groups around the world are starting to show that if you do amplitude modulated AFM experiments carefully, you can also see atoms, right? It's just you got to know the right way to do that. So I think there's still a debate in the literature about the important features of FM AFM versus AM AFM in atomic resolution. That's a story that's still evolving. And there may be a lecture at the end of the semester that tries to describe that current state of affairs. It's a really interesting problem. So this is one mode of operation. It's this constant frequency image. If you come back to the next lecture on Thursday, I'll show you some really spectacular pictures that various groups around the world have achieved using this. The other advantage of these FM, AFM tuning fork mode of operation is that you can do this force spectroscopy. right? This is something that's really interesting to, let's say, physicists, because if you can measure the shape of that tip sample force, if you can really measure it, then you can start to directly compare the tip sample force to these simple models that we discussed back at the beginning of the semester that involve van der Waals, DMT, Hertz, right? So to me, this is really a cool way to check the validity of those models to see if they're at all useful, and it's a very direct way of checking, right? There are many ways to check the validity of these models, but a lot of those checks are very indirect, right? This is a direct way because you directly measure this tip sample force by measuring the frequency shift and amplitude as you bring the cantilever from far away closer into the substrate. So this is Sater's famous formula, right? So I just to end the talk, right, I'll show you some data that we acquired here at Purdue back in the, maybe 4 or 5 years ago now, right? This is the result of attaching a sharp tungsten tip to the tine of one of these 32 kilohertz tuning forks and basically implementing this force spectroscopy mode of operation. And so what I show here is I show the amplitude of the tuning fork in the upper left panel of data. I show the frequency shift that we measured using these phase lock loops for this tuning fork as this tungsten tip was brought closer to a highly oriented pyrolytic graphite substrate. And I show measurements done for different amplitudes of oscillation of the tuning fork taken over a period of about 5 or 6 hours. So the experiment was repeated more than once, right? It was repeated many times over the course of a day. We tried to investigate different amplitudes of oscillation when the tuning fork was far from the substrate. We investigated large amplitude oscillation of the tuning fork. So the amplitude of oscillation of the tuning fork in our experiments was on the order of 7 to 10 nanometers. It was pretty large compared to the tip sample interaction forces, right? And the curve on the bottom panel of this slide shows what happens when you take those data curves in the upper panel of the slide. You use Sater's formula to interpret the data, right? When you interpret the data, you then directly get out the tip sample force as a function of the minimum separation distance between the tip and the substrate. And I think it's reasonably clear that the data is reproducible. It scales properly with different amplitudes. You can take data a few hours apart, and the tip sample interaction force is pretty reproducible during the course of an experimental run. So this is a direct measure, right? This is a direct measure of this tip sample force that we've been discussing for over a month. You can try to understand that data by fitting it to the standard models, and I just illustrate the fit that we were able to achieve here. We selected the van der Waals force. For the contact mechanics, we selected the DMT force model, right? You can see the van der Waals force gives a very good fit to the attractive regime of the tip sample interaction force. We selected the cutoff parameter A0 of about 0.3 nanometers, right? That's a parameter that has to go in to van der Waals. We also had to select the Hamacher constant, an effective modulus of the tip substrate, effective radius of the tip, right? You do all that, you use the values that we list, you can get a reasonably good fit to the van der Waals force, right? The DMT model is shown in the upper right-hand portion of this slide. It's indicated by those solid dots. If you add the DMT model to the van der Waals model and subtract it from the data, right, you get a difference. The difference that's left over we refer to as a chemical force, and it's indicated by that small smattering of points that deviate from zero for separations less than 0.5 nanometers. So it turns out this DMT plus van der Waals force allowed us to fit the data reasonably well. There's a small discrepancy, but the discrepancy is really small compared to the overall quality of the data. So I think that's the end of what I had to say today. It's just kind of how to build a frequency modulated AFM. It tries to I tried to emphasize some of the technological features of this FM AFM that kind of make it interesting. So if you're experimentally inclined, right, you may have a better appreciation of how these things work and how you might go about building one. If you come back to the next lecture, I'll show you some of the spectacular data that's been generated throughout the world using this FM AFM technology. Right, and so you'll see lots of pictures of atoms in the next lecture. So I think I'll stop now, and if you have any specific questions, I'll be happy to try to answer them. Yeah.
So when they do atomic resolution images and so forth, is that normally in air or liquids?
So in FM AFM, the primary community is ultra-high vacuum academics. Right? So most of the images that I'm going to show you in the next lecture have been taken by doing frequency modulated AFM in a very clean, ultra-high vacuum chamber. The surfaces have to be atomically clean. The surfaces have to be atomically flat, because if they're not, you're going to have difficulty resolving the atoms.
That's also why you have such a high K or stiffness, is because you can make amplitude very small as well, correct?
What's coming out of the recent literature is that as you shrink the amplitude of the oscillation of the cantilever, of the tip, as you make the amplitude of the tip oscillation smaller and smaller, it becomes a little bit easier to achieve atomic resolution. Right? So what you basically are doing is you want to make the tip amplitude oscillate in this very nonlinear tip sample interaction force. And that tip sample interaction force is essentially 5 or 6 angstroms in extent. So the tip amplitudes that scientists are using now to achieve these atomically resolved images, those tip amplitude oscillations are sub-nanometer, right? They're actually picometer tip amplitudes. And that basically means you're allowing the tip to roll back and forth sinusoidally in that very nonlinear potential well. Right? So I think the early data that achieved atomic resolution, they used larger amplitude oscillations. But as time has gone on, the emphasis has been to decrease the amplitude of oscillation of the tip, make it smaller and smaller. The tip will not stick to the substrate because the K of the cantilevers tend to be very high, right? Tend to be very high for this FM AFM, right? Yeah.
And how much vacuum?
Well, we could do a whole lecture on ultra high vacuum technology, but you're basically talking 10 to the minus 10 torr, right? So if you have a surface of metal in air and you somehow clean it off within microseconds, there's a monolayer of air molecules that coat it again. And those air molecules prevent you from seeing the underlying substrate with any great precision. So if you want to make the time it takes for these molecules to readsorb back onto a surface, if you want to make that time hours rather than fractions of a second, you have to reduce the pressure to ultra-high vacuum. Ultra-high vacuum, I think, is technically defined as anything below 10 to the minus 9 torr, but if you can get 10 to the minus 9, you can usually get 10 to the minus 10, right? So 10 to the minus 10 is a good pressure to be. Right? And these tuning forks are great because they are compatible with ultra-high vacuum. Laser photodiodes, right? These position-sensitive detectors, the lasers themselves that you use for a beam bounce technology, those tend not to be compatible with ultra-high vacuum. If you put those inside a vacuum chamber, you'll never get 10-9 torr. They outgas. They're made out of plastic. So you have to use different technologies, right, to do UHV. Takes a lot longer to do a UHV experiment. It's not something you just do on a weekend. So, but I hope you'll agree some of the results I'll show next week or next lecture are pretty spectacular. So there's at least a few groups in the world that have the money and the infrastructure to do those experiments, right? Very expensive. Very time consuming. Okay, so maybe we can assign a homework problem that should all be able to go home tonight and build an FM AFM. Right? That's what the goal is, right? If you don't know how to build them, then you don't know how to use them. Right? Okay, thanks. We'll see you Thursday.